Yeah, welcome.
So, good afternoon to one and all, dear students. Today we have Dr. Vasile Golube with us, and today we are starting a lecture series on the grid characteristics numerical method and its application to seismic wave problems. And it is very beneficial to both BTech and MTech students. And sir will discuss you, all of you, and he help you also if you have any difficulty. So now I request Vasili sir to start the proceedings. Thank you, sir.
Thank you, Juramit. So, first of all, let me introduce myself. So, my name is Vasily Golubev, and I'm currently a research scientist, senior researcher at Moscow Institute of Physics and Technology at the Laboratory of Applied Numerical Geophysics. Uh, this institute is situated in Russia, near to the Moscow, the capital of the Russia. And the goal of our group is to develop an effective method for solving a dynamic problem of deformable elastic or viscoplasticity or something like this model media. So today we start our course. The duration of the course is 1 month. We will have 4 lectures, and during this course you will be familiar with the basic concepts of numerical simulation, and we will discuss in details one particular numerical method called the grid characteristic numerical method, or the method of the inverse characteristic. This method was invented mainly for the gas dynamic problems, but my supervisor, the correspondence member of Russian Academy of Science, Professor Petrov, with his colleagues, adopted this method to the problems of deformable media. When I say deformable media, I mean that we can have some acoustic medium describe the dynamic behavior and waves inside water or some liquid, linear elasticity model to describe, for example, seismic wave propagation inside the heterogeneous geological media. This is important for seismic survey process when scientists and engineers try to find oil or maybe gas deposits and understand its structure to plan the effective exploration process. And we can speak also about the porous media to describe precisely dynamics of composites of oil deposit inside this deposit, because we have there some medium with pores filled by oil, and under the pressure we can under the dynamic pressure conditions we can obtain different waves inside this medium: pressure wave, shear wave. If we are speaking about complex models, we can obtain more than 1 or 2 or 3 different waves inside this volume. So the course was based on my PhD thesis and recent works of our group. To follow this course, I highly recommend you to install Anaconda software And the main goal for this is to obtain the access to the Jupyter notebook. As you know, currently Python is a very popular programming language, so we will use this language to write our tiny codes to illustrate some concepts. So if you have Jupyter Notebook installed, it will be enough for you. If no, please install. This software is free of charge, so you can do it. There are versions for Windows, Mac OS, Linux based system, operation system. So I hope that you will not have any problems with it. I will upload after each lecture, after each hour class, some material as a Jupyter notebook. This material, this file will contain a short description of the theory we covered, and also some practice tasks for you. I highly recommend you to solve all of these tasks as a homework, because it will be easier for you in this case to be prepared for the final questions at the exam, final exam. So let's start with some basic concepts, and I will share the whiteboard with you, and I hope that you can see my desk. And we'll start with some basic concepts. When we speak about some mathematical problem, we can say that we have some function u. This function is unknown, but we know that it depends on the time. And we can say that we want to know this unknown function u as a function of time. And it's true that we have the first order Cauchy problem. The time derivative of this unknown function u over the t equals to some function that we know, but this function can depend not only on time, but also on this unknown function itself. Of course, we think that we have an initial condition u0 or u at the time t equals to 0, and by definition we will introduce new notation for this value, use subscript 0. And of course we will speak about the open interval t is greater than 0. So we have this system, and we want to find the solution of the system. In some trivial cases, you can integrate it directly analytically and obtain the solution, like u as a function of t is some integral of f t u dt. But in this case, in fact, you have some integral equation because u is unknown. The trivial example of this problem is du over dt equals to some constant, like here -1 multiplied by this unknown function itself, and u at the time 0 equals to 0. We know how to find the solution of this equation. It's obvious that u as a function of t is exponent in the power of -t plus some constant. If you will put this exponent inside this equation, d over dt give you -1, and again u, So if we know that u at time 0 equals to u0 equals to plus constant, any value in the power of 0 equals to 1. That's why we know that c equals to 1. Sorry, minus 1, yeah? Minus 1. So you obtain something like u over the t equals to u0 minus 1 plus c. Oh, sorry, plus exponent minus t. This is an analytical solution, and we have the differential problem. This is a differential problem. Differential problem. So we can depict it as a graph. This is the value t, variable t. The point 0 we have 0, and if t equals to minus infinity plus infinity, we'll obtain here 0, minus 1. So we will obtain something like this with the asymptoty u0 minus 1. Yeah? This is the value of u. So, but what we can do if we don't know how to solve the first problem, differential problem, analytically? What we can do? We can say that we have some domain from 0 till t capital, and we will introduce here some grid Tn equals to the n multiplied by tau, where tau is the distance between the neighboring nodes, and n equals to 0 to obtain the left border of the domain till the t capital divided by n by tau, by tau, to obtain this border. So we have this set of nodes or points, and we can say that we can project our analytical solution on this set of nodes, simply putting these nodes here and calculating the values at this intersection. Yeah. So we can say that u at the time equals to n multiplied by tau equal to the un, yeah, by definition. But to estimate these values, we must know the analytical representation of our unknown function. But what we can do, we can construct something like find difference problem. Let's introduce some scheme, some algorithm, how to calculate some approximation of these values. Yeah, we can do it by our mind. We can use different approaches, like find a different method, find element method, find volume method, spectral element method, and many others. But in general, we can simply guess some iterative formula and then prove this formula will give us the correct solution of the initial differential problem, because our goal still is to solve the initial problem. What we can do? Let's think that we have some function. Yeah, we have some function, and we want to approximate somehow the first derivative. At this point, we can draw the line over the point Tn and Tn minus 1, and say that this line is a good approximation of the first derivative at this point. The real derivative, of course, is the other, but we can say that we expect that decreasing the time, the time step between Tn and Tn minus 1 will obtain the good approximation, the convergence of this straight line to the correct value of the first derivative. We will say that we have this equation and we have u, some new unknown value at the time n minus u capital at the time n minus 1 divided by tau. This is the approximation of this first derivative equals to the value f at the t n and u n. By definition, we're told that u n means u the t n, but we don't know. So that's why we will use. We don't know this analytical expression. That's why we will use some approximation like u n. Yeah, and sorry, we can use here un or un minus 1 if we want to obtain the explicit method. In any case, we put here something like this one, and what we can do, or t n minus 1 to obtain the explicit method. And of course, we have to set the initial condition u0 equals to the u at time 0 equal 0. So we know it. This is the u0. This is the correct equation. Let's deal with our initial problem 1 and write for this case u n minus u n minus 1 divided by tau equals to minus u, and let's put here the time n minus 1 to obtain the explicit method. We can reformulate it like u n is equal to the u n minus 1 multiplied by 1 plus, sorry, minus, it's my fault, minus tau. 1 minus tau. So if we know that u0 goes to the u0, we can calculate that u n equals to the u n minus 1 multiplied by 1 minus tau equals to the u capital N minus 2 multiplied by 1 minus tau squared, etc. u0 multiplied by 1 minus tau to the power of, I think, 0 for first. Yeah, I think this is correct power, the power of n. And so this is the solution of the other problem. Yeah, this second problem. let's put here these solutions. We can expect that we will not put directly inside these points, and we will obtain something like this one. Yeah, but at least we provide some procedure for the end user to obtain some values here. Yeah. And what we can do now, we can discuss what we want from this formula too. Of course, we want to obtain the solution of the initial differential problem. What we want. We want to obtain firstly the convergence or convergency. What does it mean? Let's introduce some norm, some integral difference between two functions, like L2 norm or L1 norm, or some integral of the difference, something like un minus un, and the norm. We can calculate it, for example, by summing order I un ui minus ui and absolute value. Yeah. Or we can use the integral over the t time or the domain from 0 to t capital. It doesn't matter in fact. At least we have some norm. Yeah. And we want the convergence of our algorithm, so we expect that un minus un, where un is this is values that we obtained by our algorithm. We propose this algorithm somehow, and we obtain these values. And this is a projection of precise analytical solution itself on our mesh. Yeah. In fact, we don't know these values. But what if we know? We will put it here. We calculate these values by this formula, and then we estimate this norm, and we expect that we will obtain something like O over the tau in the power of p, where p order of convergency. Order of convergency. What does it mean? It means that if we will put enough points inside our interval from 0 to t, we will obtain the correct solution. However, we don't know how to prove that we proposed the algorithm that demonstrates the convergency. How we can estimate, how we can prove it, the convergency of a proposed method. We can check two things. The first thing is the approximation. Approximation means that if we will bring the analytical solution u, and we will put directly this solution many time different that have first derivative, second derivative, third derivative, any necessary number of derivatives, and we will put it inside proposed by us algorithm directly. We will obtain the error small enough that can be estimated by tau, the step in the power of p. So let's try to check. un will be un. Okay, let's say that un minus 1 equals to the un minus 1. Let's use the Taylor expansion near to the point Tn expansion equals to Tn minus 1. T of s expansion Tn minus 1. So we will have here the derivative of the u over the time at the point Tn minus 1. Sorry, initially we have to put the value of the function itself at that point, yeah. U at the n minus 1 plus u at the point, the third derivative of the point Tn minus 1 multiplied by the distance Tn minus Tn minus 1 plus O capital over the tau squared. And this is the tau. So let's calculate un minus un minus 1. This is the un minus 1 plus the third derivative multiplied by tau plus O capital also over the tau squared minus this value un minus 1. We will obtain tau multiplied by the third derivative of the time plus O tau squared. Sorry, tau squared. Great. Now we can calculate this term. This term will be equal to tau multiplied by first derivative plus O over the tau squared divided by tau equals, for this task that we discussed, this is the u at the point for the explicit scheme we used un minus 1. Yeah. So what we have, all of these values u and first derivative of the u at Tn minus 1. So we will have all terms in the same point. T plus O over the tau equals to the u. And let's we remember the initial differential problem du over the t equals to the it's my fault, we had here minus u initially, minus u. If you compare these things and that things, you will see that the difference between these two formulas is proportional, or is approximately O over t. This is the property of our algorithm proposed. We could use the other formula here and obtain the other error term. Yeah, we can use here some special difference using u over the n minus 1 and n plus 1 to obtain the second order of approximation. But you can see that it's quite easy for us to prove that some scheme, linear scheme, has some fixed approximation order. In this case, we will have the first approximation order. But if some scheme demonstrates the first order approximation, it doesn't mean that the same scheme will demonstrate the convergency, unfortunately. The second thing is a little bit complicated. We want to have the stability. What does it mean? Stability. Stability. All of you know that if we will deal with some numerical simulation, at least we will have the error of storing our values inside the memory of the computer, according to some standard of storing values with a fixed point or float point. We will have some error connected with the representation of some value like 0, 3, 3, 3, etc. using the fixed amount of memory, 4 bytes, etc. or 6 bytes, it doesn't matter. In any case, we have the machine error precision. Yeah. So what we can do? We want, in fact, to have one interesting thing. What if we will introduce some error inside the right part of our equation? Yeah, what if we have u t equals f of t and u t equals tu plus some error of t and u. The stability means that if the error is small, the norm of the error is small. In this case, we will obtain the closed solutions obtained with our algorithm, maybe multiplied by some constant. Yeah? We can estimate the error, the difference in our solutions by the amount of error introduced. So, for example, initially we had something like this one, and after introducing some error, we will obtain something quite close. Yeah, the difference depends on the amount of error introduced in our equation. Because if our scheme doesn't have the stability, we can obtain completely different error. So fortunately, we have the theorem, the main theorem, that approximation plus stability means convergence. We will not discuss in our course how to the method of checking the stability, but there are different approaches how to check it. We can, for example, introduce some error as a sine or cosine function and obtain the area of stability for some particular scheme. But we have to know that if you want to check the convergence of the scheme, you have to test approximation, the stability, and eventually use this main theorem. So what we have to do now? I will show you briefly one more example how to check the approximation order of some specified for you scheme. The only thing is that you have to know is the Taylor expansion. I think if you don't know this technique, you can open any classic book about the mathematical analysis and read. For example, what if we have some scheme un plus 1 minus 2 un plus un minus 1 divided by tau squared plus 3 un plus 1 minus un minus 1 divided by tau plus 5 un equal to 0. And the goal or the question of this problem is to find what equation this scheme approximates and P, the approximation order. What is the approximation order? It's quite trivial. You will choose any point. It is a good idea to use Tn point because of the symmetry of all these terms, and to write the Taylor expansion near to this point, un plus t tau plus second derivative divided by 2 tau squared plus third derivative divided to 6, yeah, 3 factorial tau cube, etc. plus O or the tau 4 to the power of 4. The same for n minus 1. The same, but with other signs, yeah. T divided by tau squared minus 6 t tau plus O as a capital T4. And we will put it here. What we will obtain un plus un minus 2un 0. This one plus this one again 0. This one plus this one will obtain the second derivative. 1/2, 1/2. So totally we will obtain the coefficient equal to 1. If we will sum it, we will obtain 0. And here we will have O as a capital T to the power of 4 divided by tau squared. And we have the second derivative plus O t to the power of 2. This is the term this term approximates this second derivative with the precision tau squared. The same we will obtain here. It's approximately first derivative. Here we have, I think, with the second derivative. Yeah, the order of approximation of this formula is second. So finally, what we will obtain: second derivative plus 3 third derivative plus 5 u plus O capital of the tau squared equal to 0. So the answer to this question, the equation is here equal to 0. This is the answer to this first question, and the answer to the second question is here. The order of approximation of this scheme is 2. But if we can use this scheme to solve this problem or no, we don't know. We have to estimate the stability of the scheme initially. Okay, so let's continue. As I told you previously, we will speak at our course about the method of the inverse characteristics, or the grid characteristic method, and let's discuss the simplest case. If we have some small particles inside the water, and we will calculate the amount of particles at some fixed volume, we'll see that the change of the amount of particles Q inside this volume depends on the amount of particles go out of this volume and go inside this volume. So we can write this equation dq dt plus lambda dq dx equal to 0. This is the mass conservation law or something like this. And we can test that any function that depends on over a single variable x minus lambda t is the solution of the point of this equation. How we can test it? If we'll put this function here, we will obtain minus lambda q, the first derivative of the q, plus lambda multiplied by the first derivative of the q, and this is 0. So let's draw our domain. We have here x and we have here t, and if we know the value here, then x minus lambda t equal to the constant is called the characteristic line. We can calculate the tangents of this angle. This is the x minus lambda t equals to constant. Over this line, q is constant. Yeah, we have some propagation of our solution over this line. Was a transport equation with the constant lambda. We have a set of characteristics, with the same angles. We have here alpha, alpha, alpha. So let's add here that we have to specify, first of all, for 1D case, we have to specify one boundary condition at the left side here, something like u at the x equal to 0 and t is some u boundary as a function of t. We can change over the time in the left boundary condition, but we have to provide this condition. And second one, initial condition, something like u as a function of x at t equals to 0, u0 as a function of x. Two conditions plus the equation itself define everything. Let's try to calculate our solution. We have here x, we have here t, and we put values at some nodes here. We'll introduce the special step h, and we will introduce the time step tau. The first try is to go from this point at the current level, go for the tau time along our characteristic, but the angle characteristic depends on the equation itself, but our grid node positions depend on the some other things, like how many nodes we can store in, with our computer, or how fast we have to simulate our problem. So we will obtain something like this one. And in fact, we will obtain values at some other points. some other points here, here, here. If we deal with the linear transport equation with a constant coefficient, it's okay, in fact, because we will have the same distance between characteristic lines. But what if lambda depends on the x? In this case, we can obtain the situation like this one, the intersection of characteristics. And this will blow our solution. How to deal with this problem? The invert grid characteristic method was proposed when we have the same notations, but we fixed our mesh. We store values here. And what if we want to calculate new value at this node? We will go back along the characteristic curve that we set the special the time step small enough to be between two neighboring nodes, and we know that the solution here will be the same as the solution was previously, but at the other position. And we say, okay, we know the values at the point Tn and Tn minus 1, xn and xn minus 1, and we want to calculate the value at the point x star, here's the x star, at the moment Tn. Tn plus 1, Tn plus 1. No, it's my fault. We want to calculate the value here at the point xn at the value t at the time Tn plus 1 equals to the Tn plus tau. Yeah, we want to find the value here. We know that according to this property, this is the same as the value of u at the point x star at the intersection of this characteristic and the previous time layer, and at the point Tn, and we know that xn minus lambda tau n plus 1 equal to the x star minus lambda at Tn, because we are on this line. What we can do, xn minus lambda tau n minus lambda tau equals to the x star minus lambda tau n. So x star equals to the xn minus lambda tau. This is the position of this intersection. So we can calculate initially this point. We know xn, we know lambda, the parameter of the problem, we know tau, we set this tau small enough, and we know all values here. So in fact, we have something like u and x. We know the value u at the point xn at the time no, it's not good to use the same index, sorry, m we have to use different indexes for spatial space and for time space. XM, yeah. Now we have the correct things here. XM. U as the solution at the point XM at the time layer N, and here we know the value of X M minus 1 at this point. We'll denote it UM minus 1 N, and we have here some point X star, and we can calculate the coefficient of this line, yeah, and using the first order interpolation procedure, estimate the value of U at the point X star at the time moment Tn. How we can do it? Let's write something like we used Q notation, yeah. So we know that Q at the point M and N. First of all, Q equal to the A multiplied by X plus B, and we want to estimate this coefficient A and B. How we can do it? Qmn equal to the R multiplied by 0. We will put here the beginning of our coordinate system, plus B, and Q at the M minus 1 N is equal to the A multiplied by the coordinate of this point minus H plus B. We know these values, we know this value, so we can obtain that A equal to Qm n minus Qm minus 1 n divided by H, and B is equal to Qmn. And finally, we will obtain the formula Q at this point at the next time layer is equal to the previous value at the same point minus lambda tau divided by H Qm n minus Qm minus 1 n. This is a procedure of updating values at the next time layer. We can go from left to right and update all values using this procedure, and then we will repeat it and calculate the solution after the time 2 tau, 3 tau, etc. till t capital. So we cover the whole theory. Now I will share the screen and demonstrate you the example that I prepared for you. Okay, open. Yeah, here is the Jupyter Lab. Here I summarize some theory, and let's discuss some solutions. Here I created 11 points from 0 till 5. They have the same distance h equal to the 5 divided by 10. I set the function exponent minus t, and I plot it here. Of course, at the point 0, any exponent equals to 0 or equals to 1, sorry. And at the infinity, we will have to obtain 0. So we have the asymptoty y equal to 0. So we have this dependence. And this is the analytical solution of the problem with u0 equal to 1. Okay. Now let's discuss the explicit algorithm. This is the difference problem. In fact, the correct name of the scheme is the explicit Euler scheme. How we can use it? We have this connection. So we introduced an array that represents the amount, a set of time points. Again, 11 points and 5 is the total length of our interval t capital. We calculated dt equal to tau. We created the array to store our values of the numerical solution, yeah, u capital in our notations. We set here the initial condition at the left border. At the time equals 0, we have the value equals to 1. And then we go from left to right, started from the first component of this vector and updated it by the previous value multiplied by 1 minus tau, y minus dt. And here I put the numerical solution without connecting these points with lines, because in fact, when we speak about the analytical solution, of course, we know values at any point. We can calculate it. If we speak about the numerical solution, we have to understand that we know how to calculate at some points this numerical solution, yeah. And to compare, I put it on the same graph, and you can see that, of course, the initial point is the same, but we have some discrepancy, yeah, some difference between the positions. Here, what we can do, we can put here more points, and we will obtain the solution closer, the numerical solution that is closer to the analytical solution, because the explicit Euler scheme is stable for this particular case, and will demonstrate the convergence. Here is the example how to estimate the order of approximation of the scheme, and we can also calculate manually the order, the approximation order. How we can do it? We can calculate the error for one fixed special step, for example, tau equals to 0.2, and then we can calculate the solution for the mesh with the time step 0.1, 2 times less, yeah, and we can again calculate the error, and according to this formula, we can estimate the order of the approximation of this scheme. So the estimated order is a little bit higher than 1. That's connected with the fact that we carried out the numerical experiment. Yeah, we can obtain here some errors, because this is the estimation. This is not the analytical answer. What is the approximation order of the Euler scheme? This is some estimates of this thing. We can use the implicit method, and here I put analytical solution in green. The result simulated by the explicit scheme, yeah, with blue points, and with the orange stars, I put the result calculated on the same mesh, but using the implicit scheme. You can see that we have some differences between the answer provided by explicit scheme and implicit scheme, but in fact the total error is the same order. Implicit Euler scheme demonstrates also the first order of approximation. The main benefit is not the precision of simulation. The main benefit of the implicit scheme is the more region of stability. I will demonstrate it. Sorry, I have to run it from the beginning. Yeah. Okay. Yeah, here. What if we have 20 points and the time domain equal to 10? Let's run it. Yeah, we will obtain the same solution, explicit scheme, implicit scheme, and the analytical solution is close to both of these numerical solutions. But let's reduce the amount of points. So we will increase the special step from 10 divided by 20 to the 10 divided by 6. And let's try to run it again. So we have only 6 points and the interval equal to the 10. The analytical solution, of course, is correct. The implicit scheme demonstrate the implicit the result numerical result simulated by the implicit scheme is still close to the analytical solution. It is correct. The scheme is stable, but explicit scheme provided us the values -1, 1, -1, 1. B can see here some obviously erroneous oscillations, yeah, because if we increase the time step, we will go outside the region of stability of the explicit scheme. That's why we obtained not the solution of the initial differential problem, but some other solution. And finally, what I have to say, that this procedure that I expressed, that I explained to you, and theoretically, I implemented as the trivial tiny code for 1D transport equation. At this cell, you can see it. And initially, I set the rectangular pulse here. So in this region of the domain, we have constant and quite high concentrate of something, some particles, very tiny, that flow with a constant velocity by water. Yeah, and I used the periodic boundary conditions to not deal explicitly with the boundary conditions. So everything that go out of this domain go back from this side. And after the whole period, you can see the numerical solution obtained. In fact, if I will go, if I will put here more nodes here, something like this one, we will obtain the solution that is closer to the initial one, because analytically we have the concentration, we have the conservation of the mass, so we analytically we have to obtain the same profile, yeah, again the rectangular, but due to the errors introduced by the first order of convergency of our scheme, we obtain here some errors. But if we'll put here more and more points, we will obtain closer and closer profile of this solution. Okay, so I think that now we have to stop. Yeah, and what I have to say to you, I put here some tasks. Please think about these tasks and try to solve them. I will upload after our class this file to the cloud storage that you have the direct access to this cloud storage. Okay, I will stop the demonstration. Thank you for your time.
Thank you, sir. Students, if you want to ask something, what you feel, or do you have any problem, then you can ask.
Yeah, and I hope that Amit will share with you the video record of this lecture. Yeah, so I
Yes,
highly
yes.
recommend to watch it again.
We will upload it by tomorrow only, sir.
Okay. If you don't have any questions, in any case, we will meet here at the same place, yeah, next week. You can
Okay.
see the whole timeline of this course at our storage. Yeah, all materials that will be discussed here, you can hear, you can see at that file.
Sir, by what time they have to submit this task?
No, it is not necessary to submit this task. In fact, as we discussed at the final stage, we will have the final questions as a block at the final exam. Yeah, but if students want to be prepared for this, to answer to this question, I highly recommend at least to look through these tasks, not only watching video, because it will help them to understand deeply the concept that I presented here, and yeah.
Okay. So might
Thank you very
be
much. Yeah,
they were having questions in the next lecture,
yeah,
because
of
now they
course.
will try to learn the things and understand.
Yeah, of course.
Okay, sir. Thank you very much, sir.
Thank you very much.
Thank you,
Goodbye.
sir.
Goodbye.
Goodbye, sir. So participants, students, do you have any problem? आपको अगर कोई दिक्कत है तो अभी पूछ सकते हैं। फाइल भी सर अपलोड करेंगे, वो डाउनलोड करके आपके कोऑर्डिनेटर्स आपको सेंड कर देंगे, और आप कोशिश करिए टास्क करने की। और अगर कोई डिफिकल्टी आती है तो हम नेक्स्ट लेक्चर में सर से बात करेंगे।
Yes, sir.
तो अभी लीव कर दीजिए। थैंक यू।
Thank you, sir.
Thank you, sir.